Hello, everyone. This is Marc Ballouz. I'm the president of ISSMGE, and here we are again on a new episode of an IITT, ISSMGE International Interactive Technical Talk. This time with another exciting technical talk for regarding the Technical Committee 309 on machine learning. And this is, I think, the ninth episode. And I'm so excited to hear about it because I'm more a classical geotechnical guy, drilling foundations and shoring deep excavations. But this time I'm so excited to listen and enjoy learning from the experts with us. So today, let me share my screen to introduce the speakers. Let me see. I cannot find the speakers now. Here we are. Sharing. Yes. The speakers with us in sequence as usual from left to right is Dr. Liu, who is the actually chair of the TC309, and his expertise in machine learning and geohazards and uncertainty quantification, reliability-based design, which I think should be the design. And then we have Dr. KK uh, from the Singapore University of Technology, and he's also specialist in risk and reliability, data-centric geotechnics. Dr. Tatiana Richa, who's an expert in machine learning for the prediction of tunnel-induced settlements, very interesting. And Dr. Sara from University of Cincinnati, expert in the vital role of data selection and data cleaning in machine learning modeling for geotechnical applications. I didn't say all the titles, so we gain time. That's why I have the slide. You are all experts in this field, and I can't wait to hear about it and hear from you. I will start by giving the floor to Dr. Zhongqiang Liu, and I will stop sharing my screen. Please, Liu, start sharing yours.
Can you see my screen?
Yes.
Good. So first of all, thank you, Marc, for the opportunity to talk a little bit about the TC309 ISSMGE, and also my great pleasure to have this interaction with three other experts from all the world. Actually, at the moment, Tatiana is with me, and we are attending the conference in the Kok, this TC309 conference, the fourth one. So I'm a researcher at Norwegian Geotechnical Institute.
That's perfect timing.
Yeah, and also I'm the chair of ISSMGE TC309. I'm not going to talk about technical details for this presentation, but rather go through the TC309 activities, and we can trigger more discussions and talks. So this is a very brief overview of TC309. The technical community was actually initiated by the IIS Pass President Professor Charles Ng, and also the previous board member Dr. Susan Lakas at NGI. So this initiative actually during the board meeting in Seoul in 2017, and also at the ISSMGE closing, the board has initiated this activity, and with the growing interest in machine learning and big data, we really want to start to make use of machine learning and recent data analytics technique into geotechnical engineering and to solve our real geotechnical problems. And then we made a proposal to form this technical community, and the proposal was approved by the board right before Christmas 2017. And the technical community actually was established after after the Christmas holiday in January 2018. And I have been very enjoying the work with Muhammad and Dongming, handling this very dedicated group from everywhere. So we end up with 76 members from over 25 countries until now. And we had a lot of activities, and everybody is contributing and very active in organizing various activities. So I really enjoyed to work with them. And in terms of objectives, so we have these 4 objectives. So you can find all these details in the ISSMGE TC309 webpage. So first of all, we want to find a place to disseminate our knowledge and practice. So we organize regular webinars, and also we have different activities in this area. And secondly, we want to, let's say, we want to summarize the state of art and state of practice and make more technical recommendations. And the third one, we want to organize conference, and we want to gather everybody for discussions like we are doing in the book. And last but not least, we want to engage industry in this technical community activities, because we really know the engagement from industry is really important for us in this technical community, because normally industry is the owner of the data, but without data we cannot do anything related to machine learning. And in line with all these activities and objectives, we formed a few sub-communities, task forces, aiming to bring together all our members to be engaged in technical discussions. And we talk about different aspects. Everything is related to the investigation and application in this area of machine learning and big data in geoscience and geotechnical engineering. So we have 7 task forces at the moment. So as you can see on this slide, so we are touching on all these traditional geotechnical problems. And first of all, we want to develop benchmark database. So we want to calibrate our model and also to improve ourselves. So just make us better in this in the use of machine learning in geotechnical engineering. And we also try to apply innovative big data collection techniques to gather more data and to check the quality of the data. And also we have one tech task forces on this set investigation and soil modeling part. So we really want to use of set investigation data from the field and also from the laboratory to calibrate our more advanced soil models. And also for the design, we want to say if we could apply our machine learning pipelines into the daily workflow in our geotechnical design. And in terms of construction maintenance, I know we have a lot of data from construction and also from maintenance. So how we manage all this data and how can we use all this data? So that's really important for us. And also interact with industry and also engaged in making standards and guidelines. So how we really use machine learning in our geotechnical engineering. And recently we formed 2 new technical forces. One is physics-informed data-driven method, and the other one generative AI in geotechnical engineering practice. I know you are aware of these directions recently in our research and also in our geotechnical practice. Because normally data-driven method alone, sometimes they could provide unfeasible results, physically speaking. So that's why we want to integrate our data-driven method with our physics-informed methodologies. So that makes a more physically sound, right? And then I think you are all aware of ChatGPT. It's really, really popular at the moment. I suppose you have been trying this ChatGPT as well. Personally, I use it quite a lot. So we really want to see how we could use all these kind of new techniques in our geotechnical engineering practice. So that's the main intention for us to form these two new task forces. And then as I said, we are very proud of this TC309 conference. It's called the International Symposium on Machine Learning and Big Data in Geoscience. So it started with a very small workshop in Norway, right after the establishment of our technical community. As we can see at the bottom on the left on this slide, we gathered a few people, not a large group of members here. We gathered a few people, very motivated people in 2018. So we discussed all the possibilities of using machine learning. And this is the starting point to start this technical community conference. And then we moved to Shanghai for the second one, as you can see on the right. So we had more than 150 attendees in Shanghai, including students, researchers.
That's a very big number.
Sure. We do have
That's
a lot of
impressive.
attendees.
But just if we can go, now we know what the TC309 is doing super well. If we can start with the technical stuff because of the lack of time,
Sure.
I would appreciate it because you have to think of the viewers. They're here to hear about the technical, about the subject mainly, not
Sure.
just the TC.
Yeah. I think I work through quickly the activities, and then we start with technical presentations. Is that right, Mark? Yeah. And then we had this conference in Poland very quickly, and we had it unfortunately in online mode. So basically, we cannot show up personally. And this is a picture from our conference today, very fresh picture. And then for the machine learning dialogue, so the aim of this one is to bring together all our researchers and participants to discuss about the challenges in the use of machine learning. And then we are also working actively with young generations. So this the activity with a young member group. So we had this online event, and we attract a lot of attentions as well. And in terms of encouraging young generation, we also organize the student contests regularly together with TC304. So basically,
I love those. I love when there are student contests.
yes, we
I've
really
seen
want to engage.
some exciting stuff
Yeah,
at many conferences, and I'm trying to push forward for the international conference to have this.
sure. That's a really
Keep going. There.
yeah. And then looking back to to a survey on machine learning in geotechnics, we did the survey on machine learning in geotechnics in 2019, and we received more than 100 response, and a lot of people thought AI machine learning will likely or very likely impact our geotechnical engineering in the next 10 years. Now 5 years passed, I think we still have challenges, but we are using more and more machine learning in geotechnics. So one thing about the barriers to use machine learning, I think from this survey we learned that we don't have enough data. So data reach is really important for geotechnical engineering. How we use machine learning in geotechnical engineering, it depends on the data, right? And then another aspect is about in which area we can use machine learning. So as we can see here, site classification and monitoring observation method, they're among the top ones. So we have been hearing a lot in the conferences as well for the site investigation, for the monitoring. And it's interesting to say machine learning has less impact on design. This probably because our geotechnical design is always relying on the empirical correlations and also rely on the extra knowledge from our seniors. I think this slide brings me to the end of my presentation. I hand over to KK, I think.
Thanks, Zhongqiang. Should I just get started?
KK, you're next.
Thank you.
So much, Dr. Liu. Oh, now you made me sad not to be with you in Ireland.
So perhaps I could get started.
With you and
good
Tatiana.
morning.
I know you're both attending the TC309 conference. Yes, KK, the floor is yours.
Thank you, Mark. Good morning, Mark. Good morning, Sarah. Good afternoon, Tatiana and Zhongqiang. And good evening to myself in Singapore. First of all, thank you very much, Mark, for organizing this IITT for all of us. I just wanted to go through maybe give me about 5 to 10 minutes. I'm going to cover some of the subject matter that I've been interested for the past perhaps a decade or so, but I'm just presenting what I've been doing for the past couple of months. So I guess Zhongqiang has actually shared with us something that all of us are aware of. This idea about AI, generative AI, has really taken off. I have been attending some of these events as part of my work in the university now, and I'm just showing you what NVIDIA is doing. They are some of the stuff that they have shown me, although this is image processing, is rather incredible. So again, let me thank Marc Zhongqiang, who is the chair of TC309. I should also thank my collaborator, Jianye Qin. He is actually the current president of the Chinese Taipei Geotechnical Society. All the work are basically done with him. I just wanted to kind of like lead off this presentation to say that I've actually compiled as much as I could all the information that we've gathered so far. We've actually published a review paper in juries, and this is actually the basis of my presentation today. And it's kind of easy for me to think about this problem, and I certainly encourage all of you to raise any question if you could. But as what Zhongqiang is saying, at the apex of my structure, we have data, because without that, then we don't have to do any other things. But then I'm thinking, and I suppose Mark must be thinking the same thing. The data we are operating in is not your social media data, it's not your photograph, it's not your financial data. We're dealing with geotechnical data. That's the key. And therefore, that part is the one that links to machine learning. That's very evident. But I think the context is the one to emphasize. I'll give some examples. You can't actually analyze the data as if they are numbers, because it is through physics and experience that we get an understanding of what data is, and I'll be very specific about that. Mark would be very happy to know that I've been going around the whole world saying that the only reason for TC309 that exists is that we must bring value to practice. If not, we'll close shop. So what exactly is our value to practice? And I need to convince Mark, okay, because Mark needs to be convinced that there's some value to doing this. So he will be the person I'm pitching to, essentially. I call this the data-centric geotechnics. I want to call this a name because I want everybody not to do it as a theoretical exercise. I wanted to start out by thinking about value and context. There could be other stuff, but I think these 3 notes are very important. I've created a table, and there can be many tables to measure the value to geotechnical engineering, but I map out a simple chart looking at data on the vertical axis, looking at methods on the horizontal axis. We have only been able to look at things that I would say low-hanging fruits. You can basically, using available data, available methodology from computer science. I call this type 1. This is very simple. I think what's exciting now that we are developing, people like NGI, Zhongqiang, they're actually looking at using emerging data. These are massive data that cannot be, I think it's very hard to us to process using traditional methods, but they're massive for hazard and risk mapping. Myself, I've been working on using just available data, this is all we have now. And we develop customized a method to work with our geotechnical data. So this is obviously of interest. We have nothing that is type 3. Right? At the point, if we reach type 3, then the whole geotechnical practice would change entirely, and that is not happening now. So we don't have type 3. I want to talk about this context because I talked about it just now, and I will just show you very simple examples. 30 is a number. If it's a slope angle, the 30 is different now. You have an image. 35 is a number. 35 plus this index, that tells you something. Already you can associate 35 with the something about soft clay. 35 is a friction angle. That tells you it's a medium sand. 35 is an undrained shear strength. That's a medium stiff clay. You begin to see the numbers and meanings, and this is well known for all practicing engineers. They don't actually talk about it, but that's how you become an engineer. And of course, if 30 is less than 35, it has a lot of meaning. If it happens to be a slope angle smaller than the friction angle, you compute very quickly the factor of safety, you get that comfort level. This is an oversimplification. I want to say that there's number, there's meaning. You can't be an engineer if you don't know the meaning of your numbers. If you work just basically as a mathematical problem, this is a black box. If you think very hard, and this comes intuitively to an experienced person like Marc, he will start collating and forming numbers in his brain. And then he will realize that he's actually dealing with some of these maybe softer materials, soft clay. And Marc will be thinking that, hey, I have to worry about negative skin friction, long-term settlement. All these things is on his head, and you'll be starting to think how he can actually check and design against it. I'm just explaining what we are doing now that we are very good, and we need to exceed what we are doing now. So I hope that's very clear what context is all about. This is a problem of what we call thick data that involve this idea of context and human experience versus thin data, which is just numbers. And I don't encourage us to work on just numbers alone. If I could just, I'm going to end my presentation with a few figures to show you that I'm not just talking in the air. There's something very interesting that we could do, producing interesting results. Let me show you exactly what is this problem. At this point in time, we have a lot of databases we collected, and as what Zhongqiang says, one of the favorite problems is site investigation. So we have lots of site data. We call that a generic database. I show you a favorite diagram of mine that came from Paul Main because his diagrams are pretty. All of us are using figures of this nature. This is a generic correlation. It doesn't work for your one site. Everybody knows that. You want to use it, you got to understand the background of this. I think the challenge now is that can we combine big and small data while doing what I call it a very big challenge. Can we actually account for the differences between the sites? And of course we can. That's why I'm making this presentation, right? In fact, not only can we do it, we can do it in a very clever way. Because one thing that we are going to be in trouble if we start thinking using big database is that what happens when your database keeps increasing and it blows up? Then you're going to be, you have a computational issue, right? So that's going to be problematic. So I'm just going to show an example of how you can do it if you're clever, using the idea of quasi-regionalization. Select sites that are similar to you. Actually, engineers are doing it. I should acknowledge that this is done by engineers automatically. Select sites that are useful to you and just combine with your site. How to do it quantitatively is what I'm going to show you without maths. I call this a quasi-local, yeah, because it's not a real local correlation. So we have this standard correlation, assuming you have a few tests, say CPT, you have a design parameter, say Andrean shear strength. We do this all the time, very successful. You have a site-specific data, just 4 points. You throw it to a bunch of 1,000 points without doing any maths. This is called throwing a stone into an ocean. You get nothing. If you are clever, you only extract those sites that are similar to your current sites. Those are the green ones, by the way. You get a quasi-local correlation. This correlation is closer to the information that you want to get. The question now very clearly, what can you do to actually identify the similar sites? I'm going to show you a few figures, and then I will stop my presentation. It's very simple to see this. The big circle represents your giant database. The yellow circle represents all the sites in your database. Orange dot represents your target site. That's the site of interest. You're going to do your construction. Okay, this is the naive approach. Throw your stone into the ocean. Somehow you believe that all the sites are the same. You do something about it. So that's your standard answer. Second approach, which is done by the computer science people, why don't you try to say that the sites belong to different clusters and they're different? And then you see whether your target site belongs to one of this cluster. In a certain sense, you are restricting the universe to things that are similar. Well, it's quite useful. By the way, you also have to think about the possibility that your site don't belong to your database. So you have to be careful here. Not all data is useful. The latest that we have done now, which is something I just did about a month ago, is adaptive clustering. Take the site actually identifies sites that are similar to itself. So it's adaptive. You take a different site, you identify a different cluster. That's why it's adaptive. Let me just show you one slide why the results are useful. So this is just concept. Of course, I don't want to show you it's not useful to show you the machinery. Let me quickly show you a real database. The gray dots represents a global database. We have 7,000 odd records, about 500 odd sites around the world. The green dots represent sites only in the city of Shanghai. So it's a regional or municipal database, fairly big green dots. Yellow dots represents the target site. Is one site in Shanghai. Just to leak out a little bit of secret, yellow dots represents one site in Shanghai. Green dots represents many sites in Shanghai. Gray dots all over the world. What can we do now? If you apply the adaptive clustering, I did not use Shanghai, by the way. So I pretend that I don't know where all these sites comes from. The technique can actually pick up the blue points. It picks up the blue point, and all the blue point happens to belong to Shanghai. I did not use the Shanghai GPS information in my clustering. So this is actually validation. So the sites that are very similar, you notice that this is the city of Shanghai. You notice that the sites are actually close to the target site, which is the yellow dot. The blue dots represents the site that I've identified without any information of geographical location. I just use the soil properties. That is amazing, in my opinion. I'm very excited that I got this result. And of course, finally, just to convince all of you, if you have to use this information to do prediction, what are you going to get? If you have to use the naive approach of putting everything together, you don't care about differences between the site. Actually, many engineers will tell you can't do that, but we just put it anyway. You will get a black line representing a big uncertainty. You said, why don't I be smart about it? Because my site belongs to Shanghai. I just use the Shanghai database, all right? I'm not going to use a world database. If you do that, you'll basically get the blue line. So that is a reduction because you're using regional information. But if you're using the adaptive clustering method that I just explained, you get the green line. You notice that my uncertainty is shrinking all the time. So I am creating some value by just doing actually what all the engineers are doing, except that I'm doing it automatically. It means that you can give me a database of 1 million sites and I can process it for you. No engineer is going to process 1 million sites. You're not going to do it. That's a waste of your time. I'll stop here. Mark, thank you so much. Just to let you know, there's a workshop in Japan, end of the year. Anyone who is excited, please come to Okayama, Japan. Thank you. I'll stop here.
Where is the workshop?
The workshop is in Okayama, Japan.
Up again?
Maybe I could put it up again
Thank
very
you,
quickly.
KK. Can you guys hear me? Yes. So we can all be there.
I very much welcome you to come. By the way, I'm actually organizing a section where all the practitioners will come and share projects that they use machine learning. This is not a theoretical conference. It's focusing on engineers in Japan and all over the world. They are supposed to bring project and explain to us why the project, why machine learning is useful for that project. So this will take place 5th to 6th December.
Okayama, December.
I will send the information to all of you.
I'm going to the conference in Singapore and Hanoi and visiting also Philippines. I think it's in December. If this is
maybe
part,
we
I may be able to, so I'll do my best. Yes. Thank you,
that'll be
KK.
great.
Really exciting and
Thank you.
impressive presentation.
By the way, KK.
So our next speaker.
By the way, KK, Takayuki is with us in the Kok right now. He's attending the conference.
You can ask him to present the details.
Sure.
Thank you.
Okay, so
Next is Tatiana.
I'm gonna share my screen.
Yes.
Everything's in order? Okay. So I'm glad to be here with you today. I'm gonna present to you practical subject, let's say. It's something I worked on in my PhD that I actually defended in May. The subject is about applying machine learning for the prediction of tunnel-induced settlements. It was financed by CETEC Terrasol and CETEC TPI and organized as well by Navier Laboratories and École des Ponts Paris Tech. So it was done on the Grand Paris Express, which is today the largest metro project in Europe. We were lucky to have access to the data of line 14 South and 15 Southwest. Together, they form about 13 kilometers of tunnel excavated using tunnel boring machines, specifically earth pressure balance TBMs. So the excavation was happening in a very rich and varied stratigraphy. As you can see in the image below, we have the tunnel excavating in many different layers of soil. The biggest risk while excavating underground are the deformations on the surface. Today, we actually use traditional methods like the empirical formulas that only give a rough estimate of these deformations, or numerical simulations are very accurate, but not sufficiently reactive. Look into more rapid, more fast methods to reduce the time needed to produce and update the predictions. And that's where machine learning comes in handy. In this presentation, I'm going to focus on the prediction of the maximum settlement observed above the tunnel axis that I'm going to name SMAX. In a few words, like to simplify things, machine learning would be finding relationships between a set of features and the target based on the data. So in our case, the target would be SMAX, and the features would be tunnel boring parameters or geological parameters. We're going to be using supervised learning because we were lucky to be working on a real project where we had the monitors placed on the surface that were measuring the deformations. And we divide our data into train, validate, and test. For those of you who don't know, I might say a few words about that. So you're going to use the training, you're going to take the whole data set that we have, all the database, and we divide it into 3 parts. The first one is for training. It's where you're going to use the algorithm to go and search for the correlations between the features and the target, and it's going to create a model. And then we're going to take this model and test it using the test data set and check how good the performance is. And the validation set is actually the one used to optimize this model. Okay, that's in a few words. In order to measure the performance of the model, we're going to use performance metrics. In other words, it's just a comparison between real values, the measured ones, and the predicted ones, okay? So a good performance would have an RMSE close to 0 and R squared close to 1. Of course, there are so many different performance metrics that can be used, but in this study, we chose these two. To visualize the results, we can plot the predictions versus the real measurements. And all the values close to the diagonal would be the good predictions, and the others would be either over or underestimations. Some state-of-the-art, we're definitely not the first ones who are trying to predict settlements using machine learning. There are like 31 studies that I know of which 25 were trying to predict Smax. But there are two aspects that I want to talk about. The first one is the algorithms that are used to predict these settlements. The first test was done in 1998 by Xie et al. And we noticed that it was up until 2019, everyone was using artificial neural networks. And it's only normal, it's only logical, because XGBoost, for example, it was developed in 2014, so it wasn't well known yet. But in 2019, something happened. Someone actually discovered random forest in the geotechnical field and said, hey, I'm going to try this algorithm. And found out that random forest and XGBoost are actually giving very good performances. So the use of these algorithm was increased. The second point I want to talk about is the size of the data set. The average size of the data set used in the state-of-the-art was about 150, which is not big kind of data set to do some training for the machine learning algorithms. In our case, we were lucky enough to have access to a big quantity of data, and we created, therefore, a database. So we have to keep in mind that when we're working with field data, it's very corrupted data. The extraction of it, the cleaning, the creation of the database is a lot of work. Like in our case, it took about a year to create this database and even more. So everything is in here related to the position of on the line of the excavation. So in one position, we have all the soil parameters related to it. We have all the TBN parameters related to it, and we have all the settlement measurements around this position. We definitely cannot use all these information for our machine learning algorithm, so we had to do some feature selection. We selected different categories from the geometry, tunneling parameters, and the geology and geotechnical parameters. But the second issue we had was as I said at the beginning, that we're excavating in a very rich stratigraphy. So if we're taking like 6 geological parameters, and we have about 7 layers, and we need to take the thickness of each layer, its position for the tunnel, we can easily end up with way too many features that cannot was presented by Chen et al. In 2019, which is basically just a combination of all the mechanical properties, the thickness of the different layers, and their position in respect to the tunnel. And we'd end up with just one soil layer with combined soil parameters. And these are the ones that we're going to introduce to the machine learning algorithm. First thing we did, like everyone usually does, which is a random data splitting. Our data set was of about 2,600 observations. We divided it into 80% for the training to obtain a model, and 518 observations for the testing to make sure that the model is capable of generalization. And The small issue in this random data splitting is that we're actually considering that the tunnel already finished excavation, and we're taking all the data behind it for training and testing. And it was randomly taken on line 15 and line 14 of the Grand Paris. We compared the different results of different models, so artificial neural network, decision trees, SVM, support vector machine, random forest, and XGBoost. These two are the ensemble methods, for those of you who know. The results show that all the models have actually very good results. But if we take a closer look, we notice that the models based on decision trees like DT, RF, and XGBoost have even a better performance. However, we were really concerned about checking if these models are actually overfitting, and they are. So we had to go through regularization methods and optimization methods. For those of you who know, we use bias variance trade-off and random optimization. And another thing that I would like to add is that we varied the data set size and did the training and validation. And we noticed that we don't need like 2,000 values to do the training and have good results, but 100 values are not enough either. We need about, in our case, 700 values to have good enough results. And as I said, random splitting of the data is not very satisfying in our case, because in reality, we have a tunnel that's excavating, and we have all the data behind the face of the tunnel, and we want to predict everything that's happening in front of it. So what we want to do here is take everything behind the tunnel face for training and everything in front of it for testing. For that, we did a small test on a small portion of line 15. We took the first 1,000 meters for training and everything in front for testing. The results show that we actually have very good performances up until 300 meters in front of the face of the tunnel. And the further we go, the less the model is performant. But 300 meters is still a very good value for us, because in reality, on a daily basis, we wouldn't be able to go further than like 40 meters of excavation. So if we're capable of predicting 100 meters at a time, that would still be amazing. And we can retrain the models like daily or weekly, so that they can take into consideration new data arriving.
And I can explain the graph.
The one on the right? The one on the right, yes.
Les prévisions.
Oh, yes, predictions and measurements. Yes. Excuse me, it's in French. So as I showed in the beginning, to understand to visualize the results, we can put the predictions versus the measurements. Everything that's on the diagonal means that prediction is equal to measurement, so our model is performant. And I wanted to find a way to represent this extrapolation distance and make sure that to distinguish the points that are the nearest to the face, tunnel face, and the ones that are furthest. And that's what the color represents here. So 0 means that the point is very close to the face. And violet here, we have the points that are the furthest. So the closer we are to the tunnel face, we have values that are on the diagonal, which means that the predictions are equal to the measurements and the model is performant. And then when we go further, the predictions are going less good. And that would be it for me. I would go for conclusions. So machine learning is a reactive method because the training is extremely fast, like barely takes a few minutes. So we can always retrain it with new data. But we need data to have good enough results. And always keep in mind that the data treatment is about 80% of the work. And I think Sarah is gonna say a few words about all of this. Models can easily overfit. Always go for regularization and optimization of the models. Random forest and XGBoost are very promising for tabular data. Please go give them a chance. And the advantage of my thesis was thinking about spatial extrapolations for real-time predictions. And thank you very much.
Thank you, Tatiana. Very, very exciting real life example.
Thank
Hope
you.
to see you in Paris very soon. Are you going to be at the symposium?
I'm gonna do my best, yes. Hopefully.
Very good. Sarah, the floor is yours.
All right, thank you. So let me share my screen. And if it's coming up. It was not. Is it showing or no? Me. Can you see my screen now?
Very
So,
well,
yes.
yes.
Okay, so I want to talk in general about like data selection, and I guess Tatiana and KK already talked about it. And why data is a big deal is because we are doing geotechnical work, and it's very different from what people do in computer science. And we keep having discussions with my computer science colleagues, and when we talk about accuracy and when we talk about reliability of data, there are two different worlds, and I wanted to focus on that and see why data is important in geotechnical work and how it is different from other regions. So the first thing I want to talk about is the spatial variability in soil. So we know geotechnical properties of soil, they can change from place to place. And because of that variability, we have, some challenges. One of the challenges is when we are deciding on the feature importance. Like, the spatial variability can change it. Some features can be significant in one location, and in another location they can be less relevant or totally irrelevant. And we should be careful about it if you want to do literature review for some of the features. And it still depends on where the data is coming from and what we are dealing with in that certain location that we are studying. Another issue is uncertainty estimation, which is again because of the spatial variability of soil. So machine learning models might struggle to capture the uncertainties that are associated with the spatial variability of soil. And we want to be careful about that, especially the uncertainty in the prediction capability of the models can be higher when we have less data in a certain region. Another challenge is the data augmentation. So because each location, usually in geotechnical work, has its own geological unique condition, we cannot really say like what's going to happen even if a location is close to that location that we have the data for. So that makes data augmentation more challenging. Another one is model generalization. Can we develop a model in one location and use it in a different location? Well, for geotechnical work, there is a big question mark here because we don't know if you're dealing with the same scenario, same geological features. And model validation, I guess, you just saw in the previous presentation that when you are splitting data, there is a big chance that because you randomly select like 20-30% of data for model validation, and there is a big chance that the portion that you randomly select is not covering some of the features, or it is covering some of the features. So you can underestimate or overestimate the performance of the model. So sometimes for geotechnical work, maybe k-fold cross validation could be a better option, at least for us to make sure that the accuracy of the model that we are looking at is reasonable. It's not changing based on how we are selecting the testing training data sets. And I know this is not something that we can always do. Like a lot of the studies that people are doing these days is based on the data that is already collected. But if we are collecting data with the goal of developing machine learning models on it, we need to follow some strategies, and we need to have a strategy for sampling so that we are kind of reducing the effect of this spatial variability. But this is not an option for many of the scenarios and many of the models that we are making. Another issue that we have is limited data. Like geotechnical work, the data sets that we are dealing with, they're not as big as what we are doing, like people are doing, like when they're dealing with Twitter data, for example, or image processing. That's a huge data set, and we don't have that fancy life in geotechnical work because testing is difficult, it's expensive, and so we don't have that many data points. So one issue that this is causing is overfitting. So the models could easily be overfit. This is one crazy example that you can see RMSE is approximately close to 0 when we are doing a training, and then we move to testing and it's like 500. So this is one easy way to see that the model is overfitting. So overfitting, when we have limited data, has a higher chance. Another issue is feature selection. So when we have limited data, we cannot make sure that the data that we are dealing with is, catching all the features, and it becomes more challenging to see and assess the importance of the features when data is limited. The other one is the complexity of model. When we have limited data, because we want to avoid overfitting, we usually go with simpler models, which could be good because it's simpler models are usually more interpretable. But then the problem is, like, when we're avoiding more complex models, first, we are not using that power that is coming with machine learning, and also there is a chance that those simple models are not capturing the complexity of the underlying data. So that's another issue that we should be aware of. The model uncertainty. So when we have limited data, we might not capture all different scenarios that can happen. And because of that, then the model that we are developing, it's very uncertain. And the applicability of that model to different scenarios and new data sets, that's also going to be questionable. We have domain complexity. So geotechnical data is very complex. And when we have limited data, there is a chance that we are missing that complexity in the training data. And if you're not capturing that, then the model is not capturing that complexity. And then, the reliability of the model is under question. Hyperparameter tuning, like all these models that we are using, and sorry for the background noise, my dog decided he wants to drink. Okay, so hyperparameter tuning, these models that we are using, they have some parameters that we need to, we usually, when we start modeling, we use the parameters that are there, but then we can tune them based on the data set and what we are having. But when we have limited data, that data set might not be able to provide enough samples to robustly tune those hyperparameters. So when we do it, there is a big chance that it's not done correctly, or we are overfitting when we do hyperparameter tuning. So something that usually helps with the modeling, when we have limited data, it could be trouble. Rare events, are we capturing the rare events? If you're looking for landslide and we only have limited data, there is a chance that the model that we develop is not catching it. Another thing is, in geotechnical work, especially when we're dealing with hazards, we are focusing on the locations that we saw damages and something happened. So that's also the opposite of this, but we are more biased towards where the damage is happening. And obviously, when we have more data in those regions, the model is going to be more biased towards that. And then the model validation, obviously, with all these limitations and the limited data, the validation of the model will be questionable, and we can't really make sure that, you know, this model is doing the job that we're expecting it to do. And generalization is a part of that if you want to apply the model to a new data set, especially if you're moving from region to region. And what we can do, there are different approaches. We can do Bayesian modeling, we can do bootstrapping, cross-validation could help, and ensemble models. So these are different approaches that we can take when dealing with geotechnical work to make sure that the model is less affected by this limited data. Physical constraints is another thing that, you know, we have physical principles, and we expect different behaviors from soil material under different scenarios. And this is something that sometimes the machine learning models cannot understand, and we need an insight from a geotechnical engineer to make sure that we are not neglecting these constraints and these principles. When we do feature engineering, which means sometimes in geotechnical work, we need to translate the raw measurements into physical, meaningful parameters. And when we do that, we want to make sure that, you know, first of all, we understand soil mechanics, like the principles and geology, and it's making sense. And the new feature is, you know, the values for it are reasonable. For outlier detection, we have the same issue. Like when we are looking at outliers, we need to understand if it is really an outlier or it's just that we have less data in that range. And, you know, we want to make sure that from the geotechnical aspect, if this data is making sense or not. For regularization, which usually is done when we do machine learning modeling, you know, we get into sometimes regularization cannot help us. So we need to like incorporate the physical constraints into it so that it can also capture the limitations and the geotechnical principles, and you know, so that the model can be less affected. And then the model evaluation, you know, everybody is using R² and RMSE as a measure, but the question is that enough? Like, how much do we know from R² of like 0.9? If you're in electrical engineering, 0.9 is not even close to being good. If you're in geotechnical work, we are like, you know, 0.9 is perfect. Like we were dealing with like models that are like 0.6 or 0.5, like, you know, it's just like tossing a coin, right? So there is a big difference. How can we know? Like I say, first of all, we need to look at the results that the model is giving, and we want to make sure that you know, it's physically sound, so that the principles are followed, and you know, we are seeing the behavior of the soil that we are expecting. And also, like, residual plots are the things that
Sarah, sorry to interrupt. You have to go a bit faster.
Yes, sure. So residual plots could help us with that as well. So always consult with geotechnical people. The domain expertise, again, is focusing on the same thing. For data collection, we want to make sure we're collecting data and including important data. That is capturing all those scenarios. For pre-processing, feature selection, engineering, and validation, we also need geotechnical engineers. Like for outliers, we want to make sure that it's not just because of the sampling. And, you know, if we want to get rid of some of the data, it's not making sense that we are getting rid of it, because there is a chance that we are getting rid of points that exist and we're going to see them in future. And then if we get rid of them as data cleaning, then the model loses its predicting capability. Also, when we do feature engineering, we want to make sure we understand the meaning of it and if it's giving us reasonable results, and the interactions between geotechnical elements. Okay, so there are some soil properties that are affected by other things, and we want to make sure that we understand that when we're doing the modeling. The bias in sampling, I talked about this. You know, data augmentation is a challenge in geotechnical work. So if you're doing oversampling, I would say you want to question that twice, like think about it twice, because there is a chance that you're just not doing it the right way. And undersampling, obviously, we're going to lose some of that data, the important data. And initial approaches, I'll go quickly over it. Just 2 steps. Data visualization can help us a lot to understand what's going on with the data set and learn more about what's happening. And then data cleaning. Spend time on data cleaning because it's very important to understand what's going on. And you know, machine learning models, whatever you feed it, it's going to give you some result. So you want to make sure that you're giving it the right data, especially with those black box models. There is no way to know what's happening inside. So you want to make sure you spend time on this and you're using the correct data, and then you can trust the model that is obtained through machine learning. So sorry it took me long, but this is it. Thanks so much.
This is fantastic. Thank you so much. You know, if I look at all the presentation, they complement each other. This is the goal. I want to ask you, all of you, if, because none of you mentioned how important it is to store the data of your work. And I'm trying to promote this everywhere I go, and at conferences where I go visit with you know, lecturers and engineers. They talk about standardizing data storage in a database where each geotechnical engineer can extract data and reuse it. Unfortunately, this is not done. So there are many databases with storage of geotechnical engineers are storing their data in different places. So I hope we can manage to standardize this so your work can become easier. And of course, in my lectures, I always have a big slide where I say, don't ever show a number without the units. The units are so important. And I learned so much from you today. and I want to thank you, really. This is a great session. I wonder if you have any comments, KK or Liu, on what you heard, or Tatiana or Sarah. If you want to add more stuff, this is your chance, like a comment. Go ahead, please.
Yeah, thanks, Mark. I wonder if I could just quickly kind of like follow up on your point about databases. This is kind of important. And if you allow me, I'll just show you the TC304 website. And I think it's important that this is being shown to all the audience. This is a project that's been ongoing since 2017. And all the databases are being shared openly with everybody now. So everybody can come in and download anything that you want to for your research, for your practice. It doesn't matter. It's an open sharing by,
thank you for sharing.
By yes. TC304.
So this is on the website of the TC304?
That's correct.
Can you show the website address, please?
Okay, I'm not sure whether it's visible.
It's
www.140.112.12.21/ISSMGE/TC304.htm.
Is there a Is that a link from the main website, ISSMGE.org?
Yeah, that's right. It links to the official ISSMGE website as well.
So from the website to the TC304, and then we reach here.
You just go to the database
easy.
sublink and you get the whole page where all the data is stored in
I see
this
that.
particular website.
Friend Mark Jackson has some work done. Wonderful.
Oh yeah, this is tremendous. It's one of the most dense CPT, Adelaide. So I can't welcome everybody.
Thank you
Similar
so
to you, Mark. I've been asking everybody to submit their website so that we have open data sharing.
That's so important for our future.
Yes.
You know, you want to reduce the variability in geotechnical engineering. It goes from mayonnaise to diamonds as compared to structural engineers, for example, where the concrete cylinder can crush between 100 kilogram per centimeter square to 400. So times 4, they think it's too much. But in our case, it goes times 1,000, the strength. Maybe more. Thank you all so much. Yes. We are the best engineers, let me put it this way.